Hello, everyone. Good afternoon or good morning, depending on your time zones. I'm sorry for the delay. I had some technical issues in connecting, but I hope you can hear me and see the shared screen now. Can you please give me some feedback on that?
Yes.
Okay, perfect. So this is going to be the last lecture in the course named Supervised and Unsupervised Learning. And this is going to focus on the unsupervised part. And again, this is going to be fairly condensed or concise because of the time limitations we have. But I will try to go through the most important parts. So learning, as you have heard beforehand, has a fairly complex taxonomy. And we can talk about supervised, unsupervised, and semi-supervised learning, and even reinforcement learning. And the main difference between these areas is the type of information about the training data is given for the learning algorithm. So in case of supervised learning, we typically have labels which tell us what is the expected output, and these are most typically modeled by functions, basically thinking about the training data as a sample coming from a target function that the learning algorithm has to learn. This, you have seen a number of examples for this earlier. And in case of unsupervised learning, the landscape is very similar, but there are no labels. You only have inputs. And if you're given samples, you have to learn some kind of, I should rather say you have to uncover some kind of underlying information. And this uncovering is also called learning, a learning process. And semi-supervised or self-supervised learning are again, further variations. So if you hear about those, don't be surprised later. These include some combination of supervised and unsupervised learning, whereas in case of reinforcement learning, there are no labels, and the way the learning algorithm does get some feedback is via a reward. So whether it chooses a good action to take or a bad action will be rewarded by either positive or negative rewards. When you design a learning algorithm for a specific task that you want to solve, one thing that is important to decide on is what representation you would like to have. And representation is a key factor because the way you symbolize the data that you have, if let it be numbers or words, and if these are numbers, then you have to decide what do they denote. So whether you want to have numbers for the age of the people involved or height, and depending on the task, you can opt for a number of attributes that are available for learning, and even there you can apply several transformations. But whatever representation you go with, it's always going to be a trade-off. The smaller the representation you choose, the more efficient the learning algorithm can be. And the larger the representation you use, so the more attributes you choose to give to the learning algorithm, the larger the expressive power of the data set is going to be in order to represent what needs to be learned. Another representation question is that what hypotheses do you make about what needs to be learned? If you think that the data, the task that you want to solve does have a simple solution, so the data can be represented in simple ways, or the target function can have a simple form, then you can choose simple ideas. And they might work well to some point, but then you might realize that for more complicated scenarios or edge cases, they might not work well. And to be able to come up with a good solution for those, you might want to increase your representation power in terms of the hypothesis. So think about it as more educated expert that can have a more complicated way of thinking and can do more complex logic and is able to solve more complex subproblems. And if you choose this kind of more complex representation, then the expressive power will increase, and you will be able to learn more complicated things. And as you've seen earlier, in this later scenario, there's actually a risk that this more complex hypothesis will overfit. So in choosing the representation, this is an extremely important thing to do, to assess the necessary complexity before you choose your representation. And for each and many different representation schemes, there exist a number of learning methods. So this is just a little bit of an overview or a look back on the previous things to create context for today's discussion. And today we are specifically going to be talking about unsupervised learning. So in unsupervised learning, there are a number of subfields, but the most important ones are cluster analysis and dimensionality reduction. So these are the parts that we are going to talk about today, and that are important from an application point of view as well. So let's start with clustering. What does clustering mean? When you have data points and no labels, as I mentioned earlier, let us imagine the situation as having just 2D data points in a two-dimensional space. So basically, you can think about these as points on a sheet of paper, and therefore we can easily visualize them. So I will stick to this easy setting when talking about clustering in most of the cases, so that the visual understanding can help you develop some intuition. So the definition of clustering is basically trying to form groups of similar instances in the data set. So some of these definitely are more similar to one another than others that are more distant from each other. So the problem, and of course, forming groups is something we do on a regular basis. So developing an intuition for this is not very difficult, but forming groups is actually an ill-defined problem. So I can color these nodes to represent the groups, and you can see that I can divide them into 4 different groups, for example. And the ones that are in the same group are all more similar to one another than the samples that were put into another group. So from this point on, I'm going to refer to these groups as clusters. And what I want to illustrate with this slide is that there's no clear boundary. So here you could basically draw these boundaries. So if I want to create like where the boundaries between these clusters are, then I can just easily do that. And here basically you can see how this is lined up. But what if I think that actually these two could actually form 2 different groups and extend the boundary here to separate these 2 areas. Then this could also work well. And you could argue that the same property that the ones that are in the same cluster are more similar to one another than any of the instances from the other clusters does still apply. So this is still a valid claim. And then I could say, okay, now the number of clusters has increased from 4 to 5. And this way, we can see that choosing the number of clusters is something that is non-trivial for the clustering problem. So when we define clusters, the resulting clusters would like to give a description of this underlying structure, this underlying similarity structure of the samples or data points we have. And this is another example on a deck of cards, that if you want to cluster a deck of cards, there is no one single clustering of the poker playing cards, because you could just create 2 clusters and put the black cards in one of them and the red cards in the other group, or you could divide these further up and say that the clubs, spades, hearts, and diamonds will all correspond to different clusters. So before we start specific clustering methods, I would like to ask if you have any questions. Okay. If there are no questions, then let us start talking about specific clustering approaches. So the first one I would like to mention is called hierarchical clustering. And hierarchical clustering will start by creating as many clusters, as many samples we have. So each and every point is going to be put into its own cluster. This is how we start with. So you could basically also imagine having a little red circle around all these data points. Like I can even draw them. So like this would be one cluster, this would be another cluster, and you can just imagine that all the different points would be in a different cluster. Now, once we establish the initial clustering scheme, it's not something that is the end result. So the number of clusters, of course, is going to change, and we would like to decrease the number of clusters to a point where the eventual clusters will make more sense in terms of grouping. So to start, we're going to look at the distances between the points. And we're going to find the 2 points that are the closest to each other. And here you can see that I have colored them with a different shade. And these would be the 2 points in this sample that have the smallest distance. And therefore, we can say that these are the most similar pair of points to one another. And what we're going to do is to merge the corresponding clusters of these two. So whereas previously these had their own clusters, from this point on, their cluster will be merged, and this will be a merged cluster. And that also means that the number of clusters decreases by 1. So after merging the 2 most similar points, we have 1 less clusters than the number of initial clusters, which was equal to the number of points. And here we're going to illustrate that the 2 clusters have been merged, and we're going to represent this by this upper ellipsis, which already has 2 data points in it, whereas all the other clusters just have single elements. Now, then as a third step, we're going to, okay, this was the third step, so we merged them into a new cluster, which we also call a parent cluster. And then we're going to look at, again, the 2 most similar pair of clusters. Now, whereas previously all the clusters had just a single point, now there's one cluster that has multiple points. So when I want to determine the similarity of this new cluster to, for example, this point that is pretty close, then I have to compute the distance between the cluster and this point. And later on, we might even face situations where we have to compute the distance between clusters, each of which have multiple samples in it. Now, for the sake of simplicity, here we're going to define this distance as the distance of the closest points in the 2 clusters. So basically, if you compute the distances between all pairs in the 2 clusters, then the distance of the cluster clusters will be the minimum over these possible distances. However, let's get back to the situation where we are at the moment, and try to find with this definition the two most similar pair, clusters. So the most similar pair of clusters. And in this case, this might not be the one that we merged together in the previous round. Rather, these 2 points are probably a bit more similar, but it could be maybe these 2 points. But now for the illustration purposes, let's just accept the fact that these are the ones that are most similar. If you do this algorithmically, of course, you don't get to decide, you just compute the distances. And for whichever pair of clusters distance is minimal, you will pick those as results for step number 3, where you merge them. And then you will just keep repeating this step. And in each iteration, the number of clusters will decrease by 1. And one of the clusters will be joined with another one. So the number of instances in the 2 clusters is going to add up in that new parent cluster. So for example, this is the new parent cluster here, where we have 2 sample points coming from this previously established sub-parent cluster and a single data point cluster that was close to it. Now, if you continue this process, then you can repeat it until you are left with just 2 clusters, and even further where you merge those 2 clusters into a single cluster. Of course, that doesn't make too much sense. So at a certain point of time, you will want to stop this iteration. The tricky thing is where to stop. The nice thing about hierarchical clustering that after you finish this merger process, you will build a tree. So all these little trees will join into a single large tree, and it will be a hierarchical tree, and in each layer of the tree there's going to be one less number of nodes than in the layer below it. And the nice thing about this is that after building the whole tree, you can still decide how many clusters you would like to have. And if you cut the tree at the appropriate level, so if you imagine here that this tree was built further up, and there are many other clusters joined in here, where these all will have their respective data points, then eventually you can decide to cut the tree at different levels. You can cut it here, and then you will have 3 clusters, or you can cut it here, and then you will have more. And so wherever you cut it, you will have a very fine control over how many clusters you would like to have. And if you decide to have 4 clusters for this case, as we saw in the early example, you will find how to so what data points will belong together if you want to have 4 clusters, and the same thing will apply if you want to have 5 or more clusters. So this is a very nice property of hierarchical clustering. But for many real world applications, it will produce less favorable results. So we will also look at other techniques that can actually have more can perform more advanced grouping, and will be less prone to making mistakes in the clustering process. So, are there any questions related to hierarchical clustering? By the way, you can also write questions in the chat channel, so I will try to keep an eye on it, and thereby you don't forget whatever questions come up for you, and also others might think about those questions as well before I answer them, and even additionally they can connect to the questions by adding further aspects to it. Okay. So with that said, I'm going to move to the next method, and to motivate the next method, I will give you a very simple image example. If you think about images, the colors in of the pixels can also create groups. So similar colors can be grouped together. And in this example, we are just going to talk about grayscale pixels. And the image on the left side shows a very simple scenario where basically there are only three colors: white, black, and gray. And if you would like to cluster these pixels based on their colors, then you can look at the intensity histogram of the pixels. So for each intensity that can be seen on the horizontal axis, the vertical axis shows how many such pixels exist in the image. And you can see that the largest number of pixels are all white, then gray pixels are way less, and the smallest amount of pixels are the gray pixels. So here we have all of them. And we could label every pixel according to these intensities, which could also create a segmentation of the image. And it will all work pretty nicely. You will have all these clusters of the different objects and the background in the image. But if the image is something that you only see on a photo, then it might have some noise in it. And noise is going to make this intensity landscape a bit more complicated. So here is a simulation of a noisy input. So I added some salt and pepper noise to it. And it means that now your eyes can still see those clusters and segments in the image very nicely. But if we look at the intensity histograms, then it's different from the previous case. And not only different, but it's far less simple. They are not only just lines in the intensity histogram, rather we have these Gaussian distributions corresponding to the different intensity levels, and each and every intensity part will have just different corresponding, although similar intensities. But especially for the gray and the black, there will be pixels that have the same intensity, and still one of them belongs to the gray part and the other one belongs to the black object. So the question is how to determine the three main intensities that define these groups. And the answer is to try to cluster them. If we visualize the intensities on a 1D scale, then we can see the three groups showing up here, and the intensities are going to be different. But if we know which pixels belong to which group, we can actually compute their average intensity, and you will see that these will fall nicely into those groups. Now, our goal is to choose the three centers as the representative intensities, and we could label every pixel in the image according to which of these centers it belongs to, based on their distance. And the best way to do that is to cluster the centers. To choose the cluster centers for which the sum of square distances between all the points and the nearest cluster center is the lowest. So we want to minimize this formula. So what can we see here? The x represents the data points, and the ci represents the value of the cluster center, which this data point we want to belong to. So if I pick, for example, this point here, and I want it to belong to this cluster, then the distance of the two will be found here in the formula, and I take the square, and I do this sum of the difference between the data point and the cluster center, so the sum of the distance between the two. This can also work for in higher dimensions, so not only for one-dimensional data points. I will do this for each and every data point, and take the sum, and then also take the sum over all clusters. So this is what we refer to as SSD, as the sum of squared distance. Are there any questions here? Also, if you think that the pace I'm going with is too slow or maybe too fast, then please let me know, because I can also adjust the pace to your needs. Okay, if there are no questions, then let us proceed. So we can basically think that if we can define the cluster centers, then they will help us to get all the data points assigned correctly to the respective cluster center by minimizing the sum of square distances. So this is not very difficult, and we can expect the algorithm to produce the same result as in the previous case when there was no noise in the input. The only problem we have is that when I started the discussion, I said, if we knew which pixel belonged to which cluster, we could compute the means. And we took those means as cluster centers. But we don't know what belongs to where. So I basically assumed that I know the result when I started the whole process. So this was kind of cheating. And when we do this, then we still want to cluster to minimize this variance, but we want to change the formula in a way so that we can determine which pixel belongs where. And we're going to add this factor in here, delta I sub ij, which will influence whether a certain sample point is assigned to the given cluster that we're considering. And if we do it so, then it becomes a minimization where we are not only changing the cluster centers, but we are also changing which point belongs to which cluster. And if you are changing with these two parameters, you would like to still find where this large sum is going to take the lowest value. So for the optimal C and delta values are going to be the ones for which the sum is minimal. So this is what we call an argmin operator. So the arguments of this minimization are C and delta. And in the space of these two parameters, we're looking for values for which this so-called objective function, the SSD, takes the minimum value. Okay. But with this objective function, we are still facing the chicken and egg problem, because we will have to keep changing the deltas and the c's, which will both mutually depend on one another. So this is basically a chicken and egg problem. So as we saw earlier, if we knew the cluster centers, then we can easily allocate the points to the clusters by assigning each to the closest one. And also, if we knew which points would belong where, we could easily compute the cluster centers. And this type of formalization that we did here on the previous slide basically serves the purpose to try to alleviate this chicken and problem by formalizing it as a minimization problem over both of those parameters. And what we want to do here is to define the method how we are going to perform this minimization process. So now I'm going to quickly present you the algorithm, and then we are going to see the same thing formulated with some formulae. So the first step is that we choose, sorry. In the first step, we choose random cluster centers, but you can also take more sophisticated initial clusters, but random cluster centers will work well in most cases. Then in the second step, we are going to assign each of the remaining data points to the cluster with the closest center. So this is exactly the step that we would do as if the cluster centers were actually correct, as we saw earlier. And we are just not going to care about whether they are really correct or not. We will assign them the same way anyway. Then in the first step, the third step, we're going to calculate the centroids of each cluster center and make it the new cluster center. So we're going to do exactly just the previous step that we talked about, as if the assignments were okay. So we will calculate the cluster centers. And then we are going to iterate these two steps one after the other. So I'm going to go back to the previous slide and explain it here again. So basically, we try to alleviate this the chicken and egg property of the problem by assuming that we are almost there and doing the same iteration as if either cluster centers or the class assignments, which you can also call group memberships, would be correct, and then compute the other based on that. So in the first step, we compute the cluster centers. We compute the assignments, and we know which group belongs to the current clusters with the current cluster centers. And then we will update those cluster centers based on whatever class assignments we have now. And magically, this is going to result in a iterative process that will gradually go towards better and better clusters. So here you can see the whole thing using the formulae. So instead of having to search the two-dimensional space at the same time for both delta and C, which would be a very tedious job to do, we are just going to assume that either delta or C is fixed, which corresponds to the two types of information that we are lacking, and then compute delta based on the current C values, and then compute an updated C value, so updated cluster centers based on the currently assumed assignments, that is the current delta values. And then we are just going to repeat these two, and magically this will eventually converge. So if we look at this on a two-dimensional data set, then in each and every round, once we have the cluster centers defined, then we can create the perpendicular bisectors between those cluster centers, and that will create a so-called tessellation of the space. And whichever group of samples falls into one region of this tessellation will basically form the new cluster. And then we are going to compute the average of those points and move the cluster centers to the average or to the mean of those points, as you can see here. And then that will basically result in a new tessellation, a new decomposition of the space. And then after a while, this will eventually stop. So let me illustrate this with another example. So here we have these large number of data points, but all of them are coming from a 2D Gaussian. So these blobs were synthetically generated for illustration purposes of the operation of k-means. And if we have our input data, as I said, the first step is to choose initial cluster centers. So we can just put them in randomly. And then once you have the cluster centers, the first step is to assign each point to the closest cluster center. And as we saw this on the previous in the previous example, we can quickly do this graphically if we draw this tessellation with the current cluster centers. So for that, we only need to create the bisector lines, at least for two-dimensional samples. These are only lines. And by calculating an intersection of those lines, we are creating these regions of the tessellation, and these will correspond to the points that will belong to these randomly chosen cluster centers. Now, if you are in higher dimensions, the same thing can be done, but in those cases, these boundaries are not going to be lines, but rather higher dimensional surfaces. So for a three-dimensional input space, these are going to be planes. And for even higher dimensional data, which is something that we can't visualize, but you can always think of as a higher dimensional point as just a vector that has not 2 or 3 coordinates, but more, maybe 4 or 5 or even more, depending on the dimensionality of the data point. So in those cases, the separating boundaries will be hyperplanes. This is how we refer to these higher dimensional structures that we can't quite imagine, but I mean, we can't quite visualize, but they are still useful concepts because these boundaries will exist in higher dimensional spaces as well. But the intuition is way easier through these simple two-dimensional examples. Are there any questions? Okay, I'm not really sure if the lack of question indicates that I'm going too slowly, or you might be familiar with the material, or is everything okay? And I can proceed the way as I was going so far. Okay, well, at least one thumb up. Okay, so, but please, I beg you to either interrupt me or leave comments in the chat channel if you think I should explain something more in detail, or if I should go a bit faster because you think this is a bit too slow and boring. All right, so what's going to happen next? This was step 1 and 2, and now in step 3, we're going to compute the cluster centers by taking the average of the points inside each of the regions. So let's pick this region, for example, first. And you can see that the cluster center is here, but these points also belong to this region. So if we want to take the average of all these points, then this cluster center has definitely have to move in this direction. And similarly, this one will have to move in this direction, and this one will have to move in this direction to be able to represent these points better. Okay? And each of these cluster centers will move in some direction. And now, for those clusters that we have, these cluster centers will provide a better representation. The problem is that initially, of course, it was easy to see that because we have a synthetic data set, that these points were coming from 5 groups, and actually we indeed initialized 5 cluster centers. But because of the random initialization, I mean, the current clusters actually are not really specific to any of these initial blobs or clouds of point clouds that in an ideal as an ideal outcome we would like to have as the result of the clustering algorithm. But let's just hope for the best. So after computing the new cluster centers, we will eventually have to recreate the tessellations. Okay. Maybe at this point, I will stop for a short break, which will give you some time to contemplate over the workings of the algorithm, and then we will see how the whole process continues and where it will eventually end up. So maybe a 5-minute break here, okay? Okay. I would like to resume the class. So let us see how the updates will eventually unfold if we keep repeating these steps for this example. So to see that, we will actually turn to a specific implementation that executed this. So you will see these rectangles on the image, which actually help in the computation of the smallest distances in the iterations. But don't focus on the rectangles, rather on the colors that will represent which cluster does a given data point belong to at any given moment. And the cluster centers are denoted by these larger dots, the colored dots. And you will also see a line on the visualization, which basically corresponds to the shift the cluster center is going to make upon the update of the cluster center. So this is the cluster center before we calculate the mean of the points. And then at the end of the line, you will see the position where this cluster center is going to move to after the update. And if we make an iteration, then the cluster centers have indeed moved there to those locations. And the situation is not very bright, because even though this blob belongs to a single cluster, but these two blobs also form a single cluster, and part of this blob actually belongs to the neighboring cluster. And parts of those belong to clusters here, where two clusters actually kind of share the same blob. So we are missing a cluster for these two blobs and have at least almost a half of cluster in extra for this one. But let's see what happens with the updates. So we see that this cluster center is actually moving more towards this blob, because with this new position, only a little bit more than half of this blob belongs to this cluster center. So actually, because this blob has the same amount of data points in it, it will attract the cluster center somewhat itself than what these guys can do. And therefore, this cluster center is going to move here, but this will have an effect that some data points that were previously belonging to the green cluster will now eventually be moved further down to the purple cluster. So it seems that the purple cluster center and the green cluster centers, these two clusters are actually responsible for 3 of the blobs. And these two cluster centers, the red and the black, share a single blob. But still, the black one is visibly actually has more data points than the red one. So it's not a fair share. And also, because the red is pushed out on the edge, on the perimeters of this blob, it will actually attract a few of the points from the neighboring blob, most of the points of which belong actually to the purple blob. And if we let the process make one further step, we can see that the largest movements are still made by the green center. And this is caused by an even larger majority of the points in this green cluster belonging to this blob. So it will move further closer to these points. But by doing so, it will again lose some of these green points that it still possesses. Actually, most of the green points from this blob were already lost. So now the situation is different because previously the green and the purple were sharing almost at equal parts these three blobs. But now the purple blob has almost two complete blobs, whereas the green one has only a little bit more than a single blob. But at the same time, the green, when the purple cluster center was trying to move to the mean of these two blobs that it almost exclusively owns, it actually moved further away from these points that fall on the boundary of the red and the purple cluster. And therefore, the red cluster center could win a little bit tiny larger, a tiny bit larger share of this blob than previously. And let's just look at one further update. So not too much change, but everyone has still moved in the same direction. And if we look at the changes, the purple blob doesn't want to move too much anymore. And the green blob's vector has also decreased quite a lot. But at the same time, the vector of the red blob has increased somewhat. And if we move one further step, then we see that this actually becomes the largest one. Because now enough many points from this blob actually belong to the red cluster center that somewhere in the middle between the two blobs would be the mean of the two. So it actually has to move more towards this blob. And if it does that update, actually the purple cluster center will lose a decent number of points from this blob. And now you might be seeing what's going to happen. So the red is going to occupy this one, but by moving in this direction, it will start losing its influence over these blobs. So the black is going to take over these, and the red is going to take over a larger and larger part of this blob. So now the largest vectors belong to the red cluster center, and if we iterate in just a few number of steps, basically both the purple and the red will move to the mean of the corresponding blobs. And now there's basically a one-to-one assignment between the blobs and the clusters. So at this point, k-means stops because no further updates will be done. And the reason is that no points will move from one cluster to the other. And once that happens, then the cluster centers will not change anymore either. Are there any questions about the update process of k-means clustering? Okay, if no questions, then let's move on. So if you look at images that the colors of which you are trying to cluster, or I mean the pixels of which you are trying to cluster, you can do this either using intensity, so just based on a grayscale scenario, where you will have just intensity-based clusters, or you can do this using colors, and there you will have color-based clusters. So of course, you still get to pick the number of clusters yourself. K in K means always refers to the number of clusters, which is equal to K, which you set up initially when choosing the initial cluster centers. And it should work as a reminder that if you are the data scientist practitioner, then you are responsible for choosing K appropriately. Now, if you carefully paid attention to this previous update process, you might have wondered whether this process is guaranteed to find the optimal configuration. So is it always so that wherever you throw the initial cluster centers, they will eventually, by this update mechanism, is this update mechanism clever enough to guarantee that the cluster centers would eventually move to meaningful, would move into locations where they would own meaningful samples, creating a meaningful cluster? And the answer is no. So there can actually be cases where the optimal configuration will not be found. So on a simple set of just 3 blobs, can you think of a configuration that has converged but did not manage to minimize the distortion so that sum of square distances over all clusters and data points? So does anyone have any proposals how you could put down 3 cluster centers for these 3 data points in a way that they would not end up in the centroids, so the arithmetic mean or the center of mass or of all these blobs, or of the 3 blobs you can see here. So they would be at different positions, but still k-means updates wouldn't change, neither the locations of the cluster centers nor the assignment of the points. So, anyone?
Maybe put them all together in one point.
So if all of the cluster centers are in a single point, is that what you mean?
Yeah.
Okay. So if they are at the same location, then of course, computing the minimum from them becomes ambiguous, because for each sample in your data set, the distances from each of the cluster centers are going to be equal. And then it's going to be up to a tiebreak rule to decide. Now, in this scenario, you can basically arbitrarily or just randomly pick any of those points. There is no real theory behind. I mean, you can't really argue that any of those would be better than the other, because they are kind of equal from the point of view of the points. And if you actually happen to assign them randomly, so they take a random set of points, and then you perform the calculation of the mean, then there's a very large chance that because of this randomness in the assignment, even though they are not going to move too much, but they are going to move just a tiny bit, and then up on the next round of update, the distances are not going to be equal anymore. But this also gives you a nice insight about choosing the initial cluster centers. So once you do the initialization, instead of just randomly choosing the points, you might want to choose an initialization method where the cluster centers are somehow responsible for different regions of the input space. So try to throw the cluster centers in an iterative manner, one after the other. And whenever you put down a new cluster center upon the initialization step, try to choose a location in the input space that is far away from all the cluster centers you have already put down. And if you follow this pattern, then you can avoid such ugly situations. So I think this edge case would not end up being a stable configuration for k-means. So it would still be able to do updates and move the cluster centers. Does anyone have any other idea how the cluster centers could be placed so that they are not in their optimal position, but still no update would happen? I suspect that you assume that the next slide will show such a configuration. And therefore you are waiting patiently for me to reveal the solution. But if you want to put yourself in such a comfortable armchair, it will not help you in improving your algorithmic thinking. So maybe you could try placing one of the cluster centers here so that it would be responsible for these two blobs. And if it's in the mean of those two blobs, then this cluster center will not move. Now, where would you place the other two so that they wouldn't move either, but would not interfere with this cluster center so that this could remain stably in this suboptimal position? Anyone?
In between the other two.
Other two, there's only one further blob left. So this would be a cluster center. Let me draw it here. So one cluster center could be here. Okay, this is not it's not a very nice drawing. So, but hopefully you can imagine this. Maybe I will choose another color. So somewhere here, okay. And this would be responsible for these two blobs. So if you place the other two cluster centers outside of this, but there's only one blob left, so you have to place those somewhere inside this blob, then you might be coming a stable position, which is still suboptimal. So if those two others are all fighting for this, how is that going to look like if they end up in a tie or a draw? so that no further updates would be possible. They somehow have to share that remaining blob. So one would take one half and the other one would take the other half, right? Okay. Well, if no one is willing, then I'm indeed going to show you the solution. So this is one possible suboptimal stable scenario. Okay. All right. So what you can do to avoid such scenarios is, of course, as I mentioned previously, to do careful initialization. So if you try to move the initial cluster centers far away from one another, then you can decrease the chances of ending up in a suboptimal assignment situation. Another possibility is to do multiple runs of k-means. So basically run k-means once. And luckily, although this cannot really be proven mathematically, most data sets, the number of iterations required by k-means is not that much. So I personally haven't seen cases where k-means updates would go above 1,000. Even going above 100 is fairly rare. So in most cases, you would typically just go with a few dozens of iterations, and then you will have your final clusters. And then you can do it again. So pick new cluster centers and run it again. And in practice, the chances that you end up with a wrong configuration, so a suboptimal solution, are actually much lower than ending up in a good with a good solution, especially if you also pay attention to the first point. So go with a careful initialization. Now on the practical side, if you use libraries, k-means is present in most machine learning libraries. So, for example, you have learned scikit-learn, and that has implemented k-means clustering, and it also has built-in advanced built-in initializers. So there is one method that is called k++, as kind of a playing jokes with the C++ programming language, and if you choose one of these built-in initializers, then those are really good ways to avoid ending up in these unpleasant suboptimal solutions by k-means. Okay. So that concludes our discussion on k-means, and we're going to move on to the next method, which is mean shift. I'm going to illustrate this on image segmentation again, most notably for the reason that this was largely motivated by image segmentation tasks. And although nowadays, as it was mentioned in other courses earlier, image segmentation has more advanced methods than mean shift using deep neural networks. But mean shift still remains a cornerstone algorithm, which was published in in terms of an application. I mean, as an application for so one of its potential applications for image segmentation was published in 2002. And it was producing state-of-the-art results at the time. So what was the main advantage of mean shift over k-means? The lack of k, and I'm not joking here. So the reason this algorithm, so there's two things that you can notice in the naming scheme. One is that both have mean, so k-means has mean and mean shift has mean. And if you remember, actually k-means was also doing shift operations. So it was shifting the cluster centers to the mean of the corresponding pixels. So from this naming scheme, it's not quite clear what the difference is going to be. But in the other difference, that there's no k here, that actually tells us a bit more. Mean shift is a so-called non-parametric method, which means that you don't need to specify the number of clusters you're looking for, because that's one of the primary disadvantages of k-means. And although there are methods for k-means to come around that, namely trying clustering with multiple k's and then choosing among those solutions with different numbers of clusters. But mean shift is actually a smarter way to do this, because it can automatically find the appropriate number of clusters. And when I say automatically, we gotta be somewhat careful, because you will still have to make some educated choices or guesses. So the algorithm itself is by and large very similar to k-means. So what's going to happen is that we're going to put down cluster centers, which in this case are called seeds. And they are going to have a corresponding window. So instead of computing the tessellation, as in the case of k-means, in mean shift, we're going to assign a window to each of these seeds. And then using that window instead of the tessellation region, we're going to proceed in the very same way. So we're going to compute the mean inside the window, so basically the center of mass, and then we will shift the cluster center into that mean. And then not only the mean, but we will also shift the window, and therefore this again can become an iterative process, similarly to k-means. So the two steps are very similar to k-means, but the assignment of pixels does not happen based on, so they are not assigned to the closest cluster center, but all the pixels inside a single window will be taken account when calculating the mean. But this also means the end of exclusivity. So whereas for k-means, each pixel could only belong to one cluster, now a pixel can belong to multiple windows or fall inside multiple windows, and thereby contribute to the calculation of multiple means, which seems to be somewhat problematic, because when we say we are doing clustering, clusters are assumed to have no intersections. So in a proper clustering assignment, each and every data point has to belong to only one cluster. But as we're we're not bothered in the case of k-means to get a solution. I mean, at first we were puzzled by the chicken egg problem, but the solution around that chicken egg problem was to kind of forget about some things, namely that we don't know the cluster assignments and neither the cluster centers yet, and just mimic as if we knew and then still do the corresponding steps and then doing this iteration. Here we are also going to kind of forget about this final requirement for a while that one data point should only belong to one cluster. Now, I want to demonstrate this in a visual way to create your intuition. So at first, it's just going to be a single window. So here are some data points, and here is a window in this space. And now I take the data points that fall inside my window and calculate the average. And because, as you can see, the right side of the window has more points than the left side, so the density of the points is larger here. Therefore, the center of mass inside a window is actually to the right side. So if I calculate that, then it will fall here. And with the mean shift update, I will have to move my current cyan colored cluster center to this orange point, and that will become the new cluster center. And this arrow between the two is the shift that we are making. Okay, almost. The animation is somewhat improper. And then I will keep repeating that. So I compute the new center of mass, and I get a new vector, and I will shift the cluster center to the new center of mass, almost. So you kind of get the point. And if you do this iteration enough many times, then basically what's going to happen is that the window is going to end up around the densest region in the area, okay? So it's always going to move towards denser regions. And once it cannot move in any direction so that the density could be increased, then the window will stop here. So now let's consider a situation where it's not only a single window. So we basically put down all these many initial cluster centers and the corresponding windows, okay? So they are sort of random. We try to make sure, though, that they are not too much overlapping, okay? And then we're going to compute the means inside those windows for all of them. And because if you imagine this density distribution here as a hill, where the hill has its peak, where the densest region can be found, then basically what's going to happen that all these windows are going to start climbing the hill towards the denser areas. So whichever direction the window will see a tiny bit denser, tiny bit higher density, it will start shifting in that direction. And after a while, all of them will eventually shift somewhere close to the peak of the mountain. Now, the points that are colored blue are the ones that were all traversed by at least one of the windows when making it towards the peak. Now, if we find these windows all arriving to very similar positions or to the same position at the end, then what Minsheaf does is that it merges all those windows into a single cluster. And all the blue points, so all the points that were traversed by any of the windows that were merged into this cluster center or cluster, will basically be assigned to this cluster. Are there any questions here? Okay. So if no questions, then I'm going to proceed and see what happens next. So the remaining points were not covered by any of the windows. So we can just apply some kind of other mechanism, either trying to join them by k-means or something else, or we can make sure to cover all the data points initially by some window. So we can keep putting down windows until all points are covered. Another possibility is that instead of choosing these, I mean, here in this simple visualization, these windows were all circularly shaped. Of course, if we are in higher dimensions, then you have to go first to spheres and then to so-called hyperspheres. So in higher dimensions, these windows will have higher dimensions as well. But it's not necessary to keep these windows circular. Actually, it's not even necessary to keep them finite. So if you change these windows into Gaussian kernels, then these can extend to infinity. So basically, each window is going to cover every point in the data set, but the degree of which they belong to the given cluster will be different according to the Gaussian probabilities. So I will demonstrate this visually a bit later. But before we go there, one thing that I would like to establish is that what you can see here is basically just a single mountain. Now, in typical data sets, there's not, it's not that you would have a single point of highest density. I mean, at least locally. So there's no direction from this point in which if you could move the cluster center so that the window or the kernel would still cover the densest region. So in whatever direction you move, it's just going to decrease the density, and because of the mean is being closer to density, it's going to move back. So this is a stable equilibrium. In contrast to k-means, though, it might not converge exactly if the kernel is very large and if they are overlapping, or if it's infinitely large. So for Gaussian kernels, it might be moving tiny bits, and then the very last updates would become very small, but it would still keep on moving. And in contrast to k-means, you would not be able to detect that the updates should be stopped, because in k-means, because of the single point assignment, if If the changes become too small, then basically the cluster center updates will stop and the assignments will not change, and therefore all changes will stop immediately. Here, this is not the case. So basically, you will have to define some tiny threshold. If the changes are smaller than your tiny threshold, then you can basically stop the iterations. And if your data set is more real world, then you will have multiple such accumulation points where that are of higher density. And just staying with two-dimensional data sets, just having two such peaks in your data set, this is what you will see. So those windows that are thrown on the sides of this hill will eventually converge to this peak, and the others that fall inside this area will converge to this peak. And if these are not peaks, if you don't think about these as mountains that go high, but basins in which water can flow down, then we can think of these as basins of attraction. So all the water that is in here, so all the windows that are initialized here will eventually end up flowing down here, and these others will flow down here. So these are just inverse mountains from this point of view. So these are called basins of attraction or attraction basins. And the path on which the windows move are called trajectories. And those will basically create the points that, so they will kind of mark the points that will belong to this cluster, so that everyone inside this basin of attraction would finally be assigned to this cluster. Do you have any questions? Okay, so let me show you another visualization of this. So when we do min-shift clustering, then you can see this nice landscape, 3D landscape here, which does have many local hilltops. And you can see that the kernels thrown down will always end up on the closest hilltop. So those on the side of this high peak will climb up here, but the others will just stay around in those places. And you can see that if this is a color space, then basically the different colors will occupy different positions in the space. And if we visualize those by assigning each point the color of the cluster center, then voila, you can see all the clusters being assigned to the cluster center by having the color of the cluster center on this image. Okay. Now, if you apply this to segmentation as in the original paper, then you can actually achieve marvelous segmentation results. And this is without doing any kind of deep learning. So on the left-hand side, you can see the original images, and on the right-hand side, these, if you look closely, then you will see that the colors are quantized. So for example, here, the complete sky is of a single color. So all the clouds that existed beforehand have disappeared. And this is because of clustering. And clustering in this case means that all the pixel colors that are similar to one cluster center are changed to the color of that cluster center. And therefore, the number of colors here is just the number of clusters we have. And it's that we call a quantized color picture. Okay, and let me show you some further segmentation results. So you can see how well these work. And these are actually from the original publication. Okay. So there's one big problem though with mean shift is its computational complexity. So we need to do a lot of computations when doing the updates. And this is because we have many, many windows, and these, if the windows are finite, then the landscape is still somewhat easier. But for good results, researchers have found that it's better to have overlapping windows, or even if not infinitely large windows, so that they would have all the pixels from the image, but at least decently overlapping windows. So in this case, a lot of pixels will have to be computed into the mean, have to be taken into account when computing the mean a lot of times. And because these mean shift updates will eventually, there will be many, many shifts, actually more shifts than in case of k-means. So, and you still have to choose the termination threshold parameter. So this can actually be very computationally intensive. So when we do the updates, then we have to assign all points within the influence radius to the mode, and then assign all points within the radius of the cluster and along the search path to the cluster center, and then eventually we'll have to merge the modes as well. So even though this produced state-of-the-art results at the time, the speed of the algorithm was not very promising. So it was very, very slow. Okay. So I promised I would talk a bit about what other kernels are possible. So in addition to having spherical kernels, you can have hyperrectangles and Gaussians. And one actually widespread kernel is the Apanechnikov kernel, which assigns non-equal weights to the points that are inside the window. So the points that are closer to the cluster center will have higher weights, similarly to the Gaussian, but it is a finite kernel. So it will also have advantages in terms of being able to compute the means and the shifts. All right, I'm not going to go into the technical details or show you the equations because it would take too much time, but eventually I hope the intuition, you do have the intuition now how mean shift works, and this is what I wanted to deliver. So to sum up, the advantages of the mean shift algorithm are that it's a general purpose and application independent algorithm, and it works without assuming any models. So you don't need to know what shapes the clusters have, and they don't need to be convex. So whereas k-means will always create convex clusters because of the points being assigned to the closest center. Actually, MinShift will be able to create concave clusters, so that have curves and things like that. So moon-shaped clusters can also be nicely produced by MinShift because of keeping track of past data points that have belonged to the given cluster. And I said MinShift is called a non-parametric method, but indeed it does have a parameter, and actually multiple parameters, but the most important parameter is the size of the window and the type of the kernel, or either of those. But unlike k in k-means, which basically corresponds to the end result, so you should know something about the end result, the size of the window does have physical meaning. So it basically tells the algorithm in what range you are looking for having clusters. So if you can set the size of the window more or less to about the size of the typical objects, or to the smallest size of objects that you're looking to find, then that will produce meaningful results. And it will automatically determine the number of nodes and will behave robustly against outliers. On the cons side, we can say that the output will depend on the window size. So it's not a universal segmentation or clustering algorithm. Sorry, not classification. That's a supervised method. And selecting the window size, which is typically called bandwidth, is not a trivial task, and it is task dependent as well. It is a computationally intensive method. So here it says 2 seconds per image, which doesn't really allow for segmenting video flows. But even with more modern approaches, computation burden is still a challenge. And MinShift doesn't scale well with dimensions of feature space, where by feature space I mean that we have seen examples of creating clusters based on colors, but actually in for example, when doing image segmentation, then people do not only take into account the color of the pixels, but also the position of the pixels. So every single point will be represented by at least 5 coordinates in an image, the X and Y positional values or coordinates, and RGB for the color values if we are in the RGB color space. But actually many times people tend to use other color spaces. But it's also possible to define further features based on, for example, edges, and then the number of features can be further increased for each pixel. And therefore, it would be nice to have MinShift to behave nicely with the higher dimensionality, but the scaling of MinShift is not good for if we go towards higher and higher dimensions. Okay. Are there any questions regarding anything inside MinShift algorithm? Okay, then let's take another break. And then after the break, we will see one further clustering method and a tiny bit, at the end, I will talk about dimensionality reduction as well, so that we do mention something of that too. So let's take a short break, about 5 minutes. I'm sorry, I had an issue here, but I'm back. I hope you are still here and we can proceed with the lecture. I might speed up a bit so that we can still remain on time. What I promised to do is to cover one more unsupervised learning method, and this is called Gaussian mixture models. And these allow a probabilistic cluster assignment. So we have mentioned that in clustering, we expect each data point to belong to a cluster and preferably to a single cluster. But in some cases, especially in the previous examples, if a data point is basically very similar or has a similar the similarity score to one cluster center and to another cluster center is very close, then it's hard to decide, and there might be just a very, very tiny difference, and it might just depend on random chance or noise where it's going to belong to. And especially with k-means, where you basically decide in each and every iteration where the data point belongs, this reduces the robustness of the algorithm. Now, Gaussian mixture models basically are a more general class, and cluster belongs to a more, this clustering algorithm belongs to a more general class. And it uses an even more general approach that is called expectation maximization, which we're not going to cover in general. We just use this, and I wanted to mention that this is the bare bone mathematical framework that it builds upon. And the basic idea is of Gaussian mixture models is to generalize the k-means approach to a probabilistic setting. So it's still going to follow this two-step iteration procedure. Just the meaning and the significance of the steps will be different. And because of the probabilistic setting, their interpretation can be way more involved. I mean, more demanding in terms of mathematics, but the intuition behind them can still be developed, even if you don't understand the deep mathematics behind it. So the two steps are called the expectation and the maximization steps. And it, as I mentioned, follows the same idea to try to do iterative updates to the clusters, even if we don't know exactly which cluster does a point belong to, or where exactly the cluster is. Now, belonging to a cluster will be a bit more complicated here, because each point can belong to multiple clusters at the same time, so there will be a probability distribution. So there will be some probabilities of the class belonging here and there. It's just these probabilities have to add up to 1 for all the clusters. And in the expectation step, this so-called probabilistic cluster assignment is the thing that we are trying to improve. And in the other step, where we do maximization, that is when we are trying to find out how the clusters look like, so where exactly the clusters should be. And to put it into a bit more precise framework, basically we are trying to improve the values of the parameters that define the class. So whereas in k-means a cluster only had a center, in Gaussian mixture models, a cluster is going to be modeled by Gaussian distribution. So it's going to have a mean, which is going to be the center of the cluster, the center of the Gaussian, but it's also going to have a variance or covariances along the different dimensions, which will tell you the spread of the Gaussian and the shape, the exact shape in the high dimensional space. But the basic idea behind the updates is the same. And if we do this iterative procedure, then we can have the same hopes that this would eventually converge, even though we don't know neither the clusters nor the cluster assignments up front. So we're going to start with just random parameters, just like we did in the case of k-means. And one further similarity to k-means is that you have to pick the number of Gaussians. And we are going to denote that by k for the sake of simplicity. So we stop when the improvement is negligible. The improvement is measured in terms of likelihood. So we measure how likely that how likely it is that the given models can, so the current values of the Gaussians that we have can explain the data set that we see. And if the likelihood achieves a maximum, then a convergence point is reached. Of course, we mentioned that in case of k-means, the optimum cannot be guaranteed. And this is similarly the case for the probabilistic setting for Gaussian mixtures. So let's look at what assumptions does the GMM setting make. So as I mentioned, we have to choose the number of components. So this is not something that the algorithm can automatically determine. And if you don't know the number of clusters, then the best thing you can do is to run it with multiple values and then see either if you can visualize the results, then you might be able to choose the best one, or you can try to measure the likelihood or define other metrics based on which you can choose between these different runs. So after choosing the number of components, we're going to refer to these as omega I for the ith component. And each of these Gaussians is going to have a mean, which is going to be the central location for the component, and is going to have a covariance matrix, which will describe the spread, not only so in one dimension, this would be just a single number, which we call the variance, but in multiple dimensions, you have to give the variance in all dimensions and also how much these variances influence one another, which can be summarized in a covariance matrix. And then we are going to assume that the data set was indeed generated by these Gaussians. So this is a very fundamental assumption of the GMM model. And the way it assumes the data set to be generated, that is basically that you are given these components and the corresponding means and covariances, so the parameters of the components. And then for the generation of each sample point, you randomly choose one of the components. And according to the Gaussian distribution that is defined for it, you generate a point and you put it into your data set. So this is modeled by the so-called N stands for normal distribution, which is a Gaussian. And then mean is denoted by mu I. And for this very simple case, we just assume that all the variances are identical and each is sigma squared, which could be the variance in the first dimension, and that will be applied to all the other dimensions, and the covariant other values are all going to be zero in the covariance matrix. So there's no going, they are going to be independent basically. If they are not independent, then we can assume a general covariance matrix that is typically denoted by capital sigma, as opposed to the lowercase sigma for the one-dimensional case. And you can see that in this case, we can basically have different shapes. So not only can it be of different variance in along different dimensions, but those can actually influence one another. So these kind of ellipsoids become also possible in terms of the Gaussian. And when you draw an ellipsoid, how you should think of the Gaussians, of course, that the highest probability is in the mean, and like a distorted hat, the probability will decrease as you get further and further away from the mean. And this is basically just a line that would indicate kind of like a level where the same probability would apply for the points. So if you go in this direction, then the probabilities decrease more rapidly than in this direction. And this is caused by the variance along this axis being smaller than along this axis. So basically the uncertainty in generating the data will be larger in this direction. So are there any questions? This is only the generation part. So now I will also tell you what it will serve. But before that, I want to know if anyone has any questions. Okay. Then if no questions, then let's look at, I mean, a tiny example of what kind of inputs we might have for unsupervised learning. So sometimes it is very easy. Sometimes it is impossible, but most usually it's somewhere in between. And basically this probabilistic approach will help with this last case. So k-means could nicely solve this. No clusterization algorithm would be able to cluster this. And this one would be something that would be a better fit for example, GMM. And now I'm just going to demonstrate the workings of the algorithm through a visual example. And explain what happens through this example. So assuming that you have either initial Gaussians that you have randomly initialized somehow, or you are somewhere in the middle of the process, but you always have some parameters for all the components that you assume. So in this case, we are assuming still 3 components. We will have more data points, and each data point is basically symbolized by a tiny pie chart where the ratio of the colors of the 3 colors correspond to the amount of assigned probability to the cluster corresponding to the given color. So if we look at this data point, then what we can see that this is completely green. And this means that this data point is assumed or almost completely green. There's a tiny bit of red in it, but it almost completely assumed to belong to the green cluster. And the reason is, of course, that this is very close, and the probabilities that it belongs to the green cluster are way higher than this one belonging to the red cluster, and orders of magnitude larger than the probability belonging to the blue cluster. Why? Because the Gaussian, or the blue Gaussian, by the time you reach this point, so this is the threshold level where the same probability applies, but as you come out here, it's a very, very long tail, and it very quickly approaches zero as you get this far from the cluster center of the blue Gaussian. But you could claim that this is also outside the contour of the green one. Yes, but because it decreases very rapidly, because it's way closer to the green cluster center, therefore the probabilities are still going to be much higher. And it doesn't matter whether the absolute value of that probability is high or low, because we assume there would be three components. It's just going to calculate, it's going to assume that each and every point was generated by one of these Gaussians. And if so, then it has to belong to one of them. So even if the probability is low, but it's higher than the others, then it's going to assign the large amount of probability to the green cluster. Are there any questions related to this? Okay, so let's pick another example. So for example, this one here, which has almost an equal share of probabilities for all three clusters. And this is because it's not at the same distance from each of those, but it's, in this case, it's not the distance, but the probability level that is important. And you can see that it's very, very close to this probability level indicator, or which corresponds to the same probability level in case of all the Gaussians, which is typically 1 sigma. So this is just 1 sigma away from the cluster center. And that is the reason that the share of the probabilities is almost equal. Okay, and you can probably, I hope that you can interpret all the other tiny pie charts in a similar fashion. So we are going to do these iteration of repeating the expectation and maximization steps for the GMM model. And we are in the same type of hope as in the case of k-means, that after determining these probability values by which the points were can belong to the clusters, now we're going to update the values of the clusters. And of course, the update of the parameter values for the clusters is going to be in a way so that they would be more descriptive of the points that belong to them, so that the probabilities are also taken into account. So these very green points are going to have a large effect on the green cluster. These ones will have a somewhat more moderate effect, and these ones even more moderate effect, but they will have an effect on changing the values of the green cluster. And you see that these green points are basically more spread in this direction. So even though the green cluster is circular at the moment, but that's not warranted by any points around here. So when we update the covariance matrix, then this will basically push the circle a bit, squeeze the circle in this direction to make it narrower, because this large variance is not explained by the data points we have. And that's going to happen for both the blue and the red samples, but according to the data points they have and the probabilities assigned there. So you see that the covariance has decreased for all three clusters after just one step, quite significantly. And now the probabilities have changed quite a lot. So these points on this side of the data set have lost a lot from their green probabilities, because those were more, the green cluster was shifted towards these points on the left side, and therefore have the probability of these points belonging to the green one, especially the relative probability, have decreased. And at the same time, the relative probability belonging to the blue cluster have increased. And if you keep updating and repeating, and you can see that this is reflected in the pie chart. So the expectation step was also performed now. And if we do another M step and N step again, then the changes are now smaller, but the updates keep happening. And you see that there's still some overlap, especially between the red and the green clusters, but some data points now are clearly belonging to only one cluster, whereas others are still shared, and the blue and the red still share some part. And if you do enough many iterations, then this is going to be the final result that you get. And this is where the convergence here can only be defined again using a threshold parameter, but this is not that much difficult to choose. So if you choose 10 to the minus 3 or something like that for the likelihood, then you might have to wait a bit longer, but eventually the convergence does nicely happen. Okay, and that concludes our story over Gaussian mixture models. And you can see that this is a more advanced clustering algorithm, and it can still find meaningful clusters, more complicated clusters actually. These are still going to be convex ones, similarly to k-means, but can have arbitrary shapes, arbitrary convex shapes. And non-convex shapes can be modeled by GMM if you basically assume, I mean, you can cover the concave shapes, but by multiple convex shapes. So this is how, but this can also work for k-means. So in contrast to mean shift, which is able to internally handle concave cluster shapes, GMM is not able to do that, but this probabilistic fashion makes it a way more advanced algorithm than k-means. Are there any questions? Okay. Then I will just close this brief overview on unsupervised learning by talking a tiny bit about dimensionality reduction. So there are, I'm basically only going to give you an intuition into what dimensionality reduction typically is, and we'll show you a couple of methods, at least the names of a couple of methods, so that you recognize that those belong to this family. And if you happen to encounter them later, then you wouldn't be surprised to know that these belong to the family of the dimensionality reduction methods. So instead of having mathematics, I try to just find descriptive figure that basically tells the story. The goal of dimensionality reduction is to decrease the dimensionality of the data. And it does it by projecting attributes into a lower dimensional space. Now, because we cannot visualize dimensions above 3, or it's very difficult to visualize, so the only possibility to explain this is using the dimensions that we can visualize. So 1 dimension, 2 dimensions, and 3 dimensions. Actually, even on a screen, visualizing 3 dimension is somewhat challenging, but I hope this is still something you can perceive. So what happens when you do dimensionality reduction is that basically you try to map the data, which say is 3-dimensional, and represent it in a lower dimensional space. And this is basically as if you were projecting everything down. So you take each and every data point and move it perpendicularly towards the lower dimensional surface until you reach this plane, okay? So here you can see the green points basically have it's like a shadow. A shadow is the best everyday example of a projection. That's what happens with light. But in contrast to shadow, this still preserves the exact data points from the original location. Only in this scenario, you will have only 2 coordinates that will describe the position of the data point. And you can actually do this with the color as well, but it's a bit more difficult to visualize that and to imagine it. It's more intuitive to do this in space. And in this case, we are projecting the spatial dimensions, but preserving the color dimensions of the data points. And then if you go further and you project these down to a single dimension, then this is what you might end up with. So basically, you are trying to get rid of some attributes or reduce dimensionality because it might become easier to work with the data set. And good transformations, because these dimensionality reduction steps are carried out by data transformation operators. So a projection, it can be mathematically formulated as a transformation. So you can look at it as a function. You input your high dimensional data set into this function, and this will output a lower dimensional representation. Now, of course, when you apply this transformation, you always want to avoid losing information. So, which is always a risk, because the more compact the representation is, the more challenging it is to include the same amount of information in there. So you can see that, for example, in these projections, the colors are less vivid here because you are basically averaging out some of the points. So this can result in and of course you're losing one spatial coordinate. So this is the primary purpose of doing dimensionality reduction. But there are many different sorts of dimensionality reduction methods. Most importantly, there are ones that can be produced by just linear transformations. So where you only do multiplications and additions of the coordinates. I mean, multiplications by a constant factor and then adding that. So linear combination is just basically a weighted sum of the original combinations, coordinates, sorry. And then there are also nonlinear transformations that can have arbitrary functions and can have very complicated mappings. And here I would just I would like to show you some of the most famous dimensionality reduction methods. Definitely the most famous one would be principal component analysis, which basically is a linear rotation of the original coordinate system in a direction. So you can think of it as if you had a camera and you're rotating it and moving in a direction so that you can have a better view on your three-dimensional data. For example, if you are looking at a horse from the front, so looking it into its eyes, then you can have a much worse understanding of the shape of the horse than if you are looking at it from the side. So if you turn your camera to the side, then your visualization and understanding of the data set can become better. And there's factor analysis, which I'm not going to explain here, but independent component analysis is something that is more intuitive. This one actually tries to identify sources, the most independent sources in data that was merged previously. The very famous example for this is the so-called cocktail party problem, where you are at a cocktail party and a lot of people are chit-chatting in the room and everyone's talking. So if you have a microphone and record all these conversations, then there's going to be a huge I mean, it will be very difficult to understand any of those speeches. And still, when you are at the cocktail party, you can still have meaningful conversations with other people because somehow you are able to focus on what they are saying, just because their voice and tone has a different character than that of other people. So independent component analysis is an algorithmic approach to be able to identify the sources of the components because of their different nature. And this has a very nice algorithmic setting. And then there's non-negative matrix factorization, which is typically, I mean, the primary example for this would be, application example would be recommendation systems that you can see for all online content, like videos and posts and things like that, or even in web shops, where they try to recommend to you new items based on your previous preferences and or choices. Then autoencoders do a similar thing as principal component analysis, but in a nonlinear fashion. And then the last two items here, TSNE and UMAP, are actually dimensionality reduction methods for visualization. So they are typically used for visualization, and that makes it easy to understand something about your data set in 2 dimensions, for example, if you want to project it. But these are nonlinear methods, of course, to help you understand more about your data set. And then you can even use those mappings for further machine learning tasks. But that's another story. So with that, I would like to conclude this session on unsupervised learning. And let me just ask the very last time if anyone has any questions. Well, then I would like to thank you for your attendance. And I think this was the last course, the last lecture of the last course in the program. So I hope that you have find this useful. And please feel free to contact us even after the course if you have any questions, either in terms of the theory or in applying these in your studies or work. And we will try to help you. So thank you again, and goodbye.
Thank you, Professor. Goodbye.
Thank you for the lecture. Happy holiday.
Happy holidays to everyone.